Thank you. I'm going to introduce this. We're going to discuss lessons learned from Annex 80 simulations of resilient cooling strategies using the future climate data. Next slide, please. Just a quick overview of our simulation method. Next slide. We modeled 8 different resilient cooling strategies for both medium office buildings and single-family homes across 5 climate zones in the United States. And there were 8 strategies that we simulated. The first 2 to make the opaque envelope more reflective and cooler in the sun. Then we looked at solar control strategies for windows. We considered both fixed and operable window shading systems. Then we looked at variations on natural ventilation, changing the opening area and changing the operating schedule. And we also considered ceiling fans for increased air motion. We covered 3 different vintages: current buildings, post-1980 buildings, and pre-1980 buildings. And we did this work in 6 different climates in the United States. Now, the red text here shows those strategies, categories, vintages, and cities that we're going to discuss in today's presentation. And for the benefit of a venticool audience, we've decided that natural ventilation should be one of these. But we'll also look at ceiling fans for the benefit of increased air motion. We're going to focus on the medium office building arbitrarily. We're going to show results for both current buildings, which are typically tightest and best insulated, but also for oldest buildings, because over half of the buildings in the United States were constructed before 1980. And we're going to look at Los Angeles because we have past, present, and future climate data for that city. And now I will turn it over to Sang-Hoon.
Hi. For the Annex 80 work, we use US DOE reference building energy models, and also we use EnergyPlus as a simulation engine. So in this presentation, we focus on the medium office building. As right figure shows, the medium office model has a 3-story building and total floor area about 5,000 square meters. Each floor has 1 core zone and 4 parameter zones for each orientation. The window area is about 33% of the total envelope area. So HVAC system is serving each zone with a DX system for cooling and gas furnace for heating. So we modeled 3 vintages for pre-1980, post-1980, and current vintage. So envelope properties and HVAC system, internal heat gains, and infiltration, those were updated to represent these 3 vintages. This slide shows the US map with climate zones. For the Annex US work, we selected 6 locations. But for the presentation today, we focus on the simulation results for the Los Angeles with 4 weather data. So we used 4 weather data to cover past, current, and 2 futures. The past weather is based on the TMI3 data, so cover 1991 to 2005. And the current weather and the future weather data were generated based on the Coldex approach. So the current weather data, Coldex 2010, covers 2001 to 2020, and Coldex 2050 is for the midterm future, and Coldex 2090 is for the long future. So as we expect from the global warming, the annual average temperature and heating degree, cooling degree days rise in the future, but heating degree days decline in the future. But however, the red dotted line shows some inconsistency here. So for example, Coldex 2010 shows annual average temperature smaller than the TMI3 and heating degree days are greater. So which means the current weather with Coldex 2010 is cooler compared to the past weather with TMI3. And also somehow solar radiation data from the Cordex inconsistent. In the previous presentation, Agnes mentioned a little bit here, but we found that less solar radiation in the future. So this makes the simulation results not consistent with temperature rise in the future. So with that, so we decided to use the same solar radiation for our simulation. So the the radiation values in the table were replaced with Cordex 2010 data. And HVAC system sizing matters when dealing with future weather data and simulations. So we used sizing based on the TMI3 weather data. As Ronnen mentioned in the earlier slide, the simulation scope covers 8 resilient cooling strategies with various cases and 2 building types with and without air conditioning, and 3 vintages and 6 locations and 4 weather data for Los Angeles. So this results in more than 10,000 simulation runs. So we needed a pipeline to model all the scenarios and simulate them and do post-processing to take care of the simulation results. So for this, we used jePlus for the modeling to link with EnergyPlus simulations, and we developed custom Python code for post-processing. Now we will show some baseline simulation results for the medium office model in Los Angeles. So we modeled the baseline with cooling system and without cooling system. The model with cooling system is used for the cooling energy analysis, and the model without cooling system is used for thermal comfort analysis. The left plot shows annual cooling source energy intensity, and the right one shows the annual warm discomfort hours. X-axis shows the vintages, and 4 different colored lines represent simulation results from 4 weather data. So if you look at the left figure, the newer vintage models show less cooling energy as newer buildings are more energy efficient, but the models with future weather have more cooling as the future weathers are hotter. And if you look at the right figure, thermal comfort improves from the oldest to older vintage, but not in the current vintage. So this is caused from the less infiltration and low U value envelope and heavier thermal mass in the current vintage, as they contribute to hold warm air in the newer buildings. And also it shows that the future weathers show more warm discomfort hours. And also I can point out that warm discomfort hours from Cordex 2010, the yellow line, and is slightly smaller than actually the TMI3 data. So this is basically caused from the Cordex 2010 weather data. Basically, Cordex 2010 is cooler than the TMI3 data. Now let's check some natural ventilation strategy. So natural ventilation provides cooler air, and this helps save cooling energy and improve thermal comfort. So we modeled 6 cases. So case 0 is for the no natural ventilation. Then we increased the opening area percentage from 2.5 and up to 50%. A key for the natural ventilation modeling is when to open windows. So for this modeling, we assumed window openings are only allowed when outdoor air is in between heating and cooling set point temperature. This slide shows cooling energy savings. So left plot is for the oldest vintage outcome, and the right plot is for the current vintage. X-axis shows the fraction of the window's opening area, and the 4 different color lines show how cooling energy savings change from the weather data. So the base case is no natural ventilation, and it shows cooling energy saving in a way non-linear with more windows opening. And it shows that cooling energy savings are mostly realized from just opening windows, then saving degree is reduced for more openings. And natural ventilation strategy is more beneficial in the future, so it can provide up to 56% more cooling energy savings compared to the TMI3 weather data, looking at the Cordex 29 here. And this slide shows thermal comfort improvement. The plots show how many warm discomfort hours can be reduced from window opening. And it shows that warm discomfort hours can be reduced significantly from the small openings. Then reduction degree is reduced also for more openings. So natural ventilation provides greater discomfort reduction in the future. So it can provide up to 59% more warm discomfort hours reduction compared to the TMI3 data. So the current vintage and old vintage, all these vintage show the same trend. Now let's move on to the ceiling fan strategy. So ceiling fan increases air movement near human skin, and it improves thermal comfort and allows raising the cooling set point temperature. So case 0 represents no ceiling fan. Then we modeled various ceiling fan cases that increase air speed from 0.4 up to 1.6 meter per second. Cooling set point temperature is increased accordingly with the increased air speed. Plots show cooling energy savings from the ceiling fan strategy. So cooling energy savings show also nonlinear when air speed is increased. The savings from the increasing air movement from the no ceiling fan to 0.4 meter per second is about half of the savings compared to the maximum ceiling fan speed, which is 1.6 meter per second. The 0.4 meter per second ceiling fan is from the low speed ceiling fan. So this means that the low speed ceiling fan can save cooling energy effectively compared to the no ceiling fan case. And ceiling fan contribute to more cooling energy savings in the future. So it provides about 30% compared to the TMI weather data in the long future. This slide is for the plot for the warm discomfort reductions from the ceiling fan strategy. Also, discomfort reductions show nonlinear. And again, the low speed ceiling fan help to reduce discomfort significantly. It also shows that ceiling fan strategy is beneficial in the long future to reduce warm discomfort. Yeah, also I want to mention that the Cordex 2010 data shows negative reduction compared to the TMI3. So this is simply because the Cordex 2010 weather data that's cooler than the TMI3. So we have two key takeaway slides. The first one is about the simulation results. So future weather matters. With our simulation study, natural ventilation and ceiling fan can save cooling energy up to 56% and reduce warm discomfort hours up to 59% with future weather data in Los Angeles. And we presented outputs from two vintages, pre-1980 and the current vintage. So fractional increases in the cooling energy savings and warm discomfort reductions were similar for two vintage models, but though the absolute savings are greater in the oldest vintage. More cooling energy savings and warm discomfort reductions are realized in the hotter weather. So in this study, Cordex 29 has the greatest changes. And some key takeaways from the simulation process. And solar radiation data matter in the simulation results. So when dealing with the Cordex and or other weather data, so we need to check and resolve any unexplained changes in the solar radiation data. And also when checking the weather data, check the annual average temperature and the cooling degree days and heating degree days for the future weather especially, and verify they all make sense. So we recommend to use the latest version of the EnergyPlus. Recently, EnergyPlus team resolved some errors in the PMV calculation and also added some thermal resilience metrics. Also, I want to mention that jePlus is very useful when dealing with this kind of parametric one with EnergyPlus simulations. Other than that, simulation process is straightforward. I think this is our last slide. Thank you.